So today I'm going to cover the beginning of section 4.8, 4.81, which is about another probability distribution or another random variable called the geometric random variable. This will occur when we play the following game. Suppose we have a biased coin, probability of heads is P. So the probability of tails is 1 minus P. And we play the following game. We flip the coin over and over until we achieve heads, success, or till we win heads. And then, so we can ask what does this random variable look like? What is its probability mass function? What's its expectation? What's its variance? And that's what we're going to do today. Okay, so 4.8 is called other probability distributions. And we are in section 4.81, which is called the geometric random variable. Okay, so we have Bernoulli trials. Where the probability of success is P, so the probability of failure is 1 minus P. And let X be the number of performances of the experiment that we have to perform until we get heads. So number of times experiment, in this case, tossing a coin maybe, until success. So what is the probability? What is P of n, the probability mass function? That's the probability that X is n. And well, you have n minus 1 failures, and then that would give you a 1 minus P to the n minus 1. And then you have a single success, that would give you a probability of P. So that is what the probability mass function looks like. And in fact, this is a PMF. Let me circle this. Why is this a PMF? Because if I take the sum of P of n, n goes from 1 to infinity. So what is the sum of the sum? We want to get 1, right? So this is the sum of 1 minus P to the n minus 1 times P, n goes from 1 to infinity. We can factor out a P, and then we get the sum of 1 minus P. Let's reset n. Let's set j equal to n plus 1. So this would be the sum. Oops, I think I want n minus 1. In fact, this is the sum. J goes from 0 to infinity of 1 minus P to the j times 1 minus P to the j. And here j is equal to n minus 1. Okay, so now this is a geometric series in here, and its common ratio is 1 minus P, so you get 1 minus the quantity 1 minus P, so you get P times 1 over P, and you get 1. So this checks out. It is a PMF. It is a probability mass function. Let's do an example of this. Suppose and this is in the text, let's have an urn with M balls colored white and N black balls. And we select balls without replacement. actually, without replacement until I meant with replacement, sorry. Until success, until a black ball is chosen. That's success. So that's the experiment. And we want to, so we keep, the experiment is to select a ball. And so we want to figure out the number of times, want to figure out what the PMF is in this case. So this is the number of draws, the number of selections we have to make. And so what is the probability of success? Well, there are, I actually, the book does this backwards. I want, it lets N be the number of white balls and M be the number of black balls. So I'm going to follow the book in this case. So yes, so it's going to be M here and N here. So how many balls are there totals? There are M plus N balls in the urn. Now, if I randomly select a ball, what's the probability that it's black? Well, there are M black balls, so it's M over M plus N. And the probability of failure is, you could either take 1 minus that number, or you could just compute it directly. It's N over M plus N. Okay, so now what's the probability that X is equal to N, which is, this is give me the probability mass function. Well, you have, first of all, a bunch of failures, N minus 1 of them, so that would be N over M plus N to the N little n minus 1, and then we have one success, that would be an M over M plus N. And with a little bit of arithmetic or algebra, you see that this is the same thing as M times N to the N minus 1 over M plus N to the power of N. Okay, so that's the first thing. Let me circle that. That's P of N. Okay, what about the probability that, this is actually part A of the question. There's a part B. What is the probability that X is at least K? Well, that's the sum. K goes from N to infinity P of N, which is the sum of M M N to the K minus 1 over M plus N to the K, and K is going from N to infinity. Okay, and we can factor out an M over M plus N from this expression to get the sum. K goes from N to infinity of N to the K minus 1 over M plus N to the K minus 1. And what is that? Well, that's the same thing. See, this thing here is a geometric series. Which starts off when K is N, but the K minus 1 is here. So let me rewrite this, and you'll see that this is the same as M over M plus N times, okay, so remember the sum of a geometric series A plus AX plus AX squared, etc., is A over 1 minus X. So this is going to be M over M plus N. Okay, the first term when K is N gives me the first term. That's my A. and it gives me an n over m plus n. The first term is a k minus 1, and then we have to multiply it by a 1 over the common ratio here, which is n over m plus n. That's the thing you're multiplying by. Okay, so what do you get? You're going to get, if you multiply all this out, you'll see that this becomes, and I'm going to spare you the arithmetic, it becomes n over m plus n to the k minus first power. That's the answer to this. So that's the answer. So that is the probability that x is at least k or more. Okay, so now for the rest of this lecture, what I'd like to do is compute the expected value or the expectation of the geometric random variable. By the way, the geometric random variable is any random variable with this probability mass function outlined on the previous slide. So I'll review that on the next slide. So let's do that. So a random variable x is geometric if its probability mass function p of n is given by 1 minus p to the n minus 1 times p. So that's the definition. Okay, so now let's compute the expected value e of x. That's the first problem. Well, that's the sum. K goes from 1 to infinity of k times p of k, which is going to be given by k. Okay, it's convenient to set q equal to 1 minus p so that p plus q equals 1. So now 1 minus p is given by q. So we get q to the k minus 1 times p appearing. And this is the same as p times the sum. K goes from 1 to infinity of kq to the k minus 1. Okay, so now let's recall the following formula. If we take 1 plus x squared, etc., that's 1 over 1 minus x. I'm assuming the absolute value of x is less than 1, and if we differentiate, we're going to get 1 plus 2x plus 3x squared, etc., is the derivative of the right side, which is 1 over 1 minus x quantity squared. And so if we apply that here, this is the left side is the sum. K goes from 1 to infinity of kx to the k minus 1. That's what it is. And so we know that that's 1 over 1 minus x quantity squared. And so I can take that, what I just did, and substitute it into the formula that I've been trying to derive. I get p times, here x is q, so it's going to be 1 over 1 minus q squared, or in other words, p times 1 over p quantity squared, because 1 minus q is p, and we get 1 over p. So the expected value of our random variable, our geometric random variable, is 1 over p. So that's kind of simple. Okay, so that's the expected value. I'm going to now turn to computing the variance, but in order to do the variance, I have to compute the second moment first. So that's my next step. Okay, so let's consider the expected value of x squared. That's the second moment. And by definition, that would be the sum. K goes from 1 to infinity of k squared q to the k minus 1 times p. And again, q is 1 minus p. Okay, now we're going to do a trick here. The trick is this. K squared is k minus 1 plus 1 quantity squared, and that's k minus 1 squared plus twice k minus 1 plus 1. I'm thinking of k minus 1 as like a variable, and then I just do the binomial expansion. Okay, so what do you get here? So this is the same as the sum k goes from 1 to infinity of k minus 1 squared plus 2k minus 1 plus 1 times q to the k minus 1 times p. And that I'm going to break this up into three terms. There's the first term involving the k minus 1 squared. I'm going to bring a p through the summation. So it's p times the sum k minus 1 squared times q to the k minus 1. I actually think I want to put the p back in. Okay, and then there's going to be twice, and then k minus 1 to the first power times q to the k minus 1 times p. And then the last term is the sum, and here k is going from 1 to infinity, k is going from 1 to infinity, k is going from 1 to infinity. The last term is q to the k minus 1 times p. Okay, the first thing to note is that this term here is by definition the sum of p of k, the sum of all the values of the PMF. So it's the sum of p of k, and that's 1. So this term is 1. Okay, so I'm allowed to substitute 1 there. Okay, the second thing to note is we can reindex this expression here in the middle, and that's twice the sum j goes from 0 to infinity of j times q to the j times p. Okay, so that's what you get there. And lastly, this term here is the sum. So j here is k minus 1. And similarly, this is j goes from 0 to infinity of j squared q to the k minus 1 times p. So what do we have? We have that. Okay, so now if you think about it, this expression here is just given by, oh, I forgot to note that this is a j also. So let me put that in. Okay, so what I'm going to do is bring a copy of q through here. So at the expense of making the j into a j minus 1. So I can take a factor of q and bring it outside. You'll see why. And similarly here also. So if you think about if you do that, what do you get? You're going to get q. Now this expression here, this first summation, is exactly the same thing as the expected value going back to the top line of x squared again, the second moment. And the second summation is given by the expected value of x by definition. And then we're going to have to add 1. Okay, so what does this tell us? This tells us, I'm going to rewrite this all out now. It tells us the expected value, the second moment, that is e of x squared, is qe of x squared plus 2qe of x plus 1. So let me write that out. So what do you get? We get e of x squared is given by qe of x squared plus 2qe of x plus 1. And what I'm going to do is I'm going to bring the second moment terms over to the one side. So it's 1 minus q e of x squared equals 2q. Now we computed e of x and we got 1 over p before. Okay, and then we have to add 1. And note that 1 minus q, since q equals 1 minus p, p is 1 minus q. So p e of x squared is 2q over p plus 1. Or in other words, e of x squared is given by 2q over p squared. I'm dividing both sides by p plus 1 over p. Or if you like, 2q plus p over p squared. So that's the second moment. And from this, we can easily compute the variance. So the variance of x is given by 2q. So it's e of x squared minus the quantity e of x quantity squared. And that's going to be, so what is 2q plus p? 2q plus p is 2, let me do this in a different color. This is 2 times 1 minus p plus p over p squared. And this becomes what? So it becomes 2 minus 2p plus p, so 2 minus p over p squared. Okay, so what do we get? So the expected value of x squared is 2 minus p over p squared minus the quantity. Let me do this in black again. Minus the quantity e of x quantity squared, so that's 1 over p squared. So we get 2 minus p over p squared minus 1 over p squared. And in the end of the day, the variance of x is going to be given by 1 minus p over p squared. So that is the final answer, the variance of the geometric random variable. So whenever we have a new random variable, the first question we get is what is its, one of the first questions we get is how to compute its expected value and how do we compute its variance. And we've done that in each case so far. Okay, so that's good enough for today. And we will continue with the rest of this section next time. Have a good one.